right? Or the rings, they'll have rings that do it, you know. Who knows what they're going to have? It'll be kind of funny. So, all right, organic chemistry. That's what we're doing. Now, let me tell you my ignorance. I did not like organic chemistry when I was in college. I didn't understand organic chemistry when I was in college. And therefore, when I started teaching this class, I had to teach myself organic chemistry before I could teach the students because I didn't remember any of it. I mean, I'd had the class, I'd had organic chemistry, but that had been 20 some odd years before, and I didn't learn it then, so I had to relearn it. So let me just say, for those of you that are of the nature as we start this, you're like, oh my goodness, this is another language, I hate this. You are not alone. But there will be others of you that will be like, this is a piece of cake. Why do people say this is hard? This is easy. I understand this totally. And I'm happy for you. But for the rest of us, you're going to have to spend time with it, okay? So every day, this is what we're going to start off doing. Every day, we're going to go through the functional groups because that's how I learned them. I learned the functional groups by going through them every morning before I got out of bed. I would lie in bed and I would just literally go through those tables in my head. And that's how I learned them. So that we're going to learn them every day. We're going to work on them. So tell me, get your table out. Have your table out so you can do it with me. I may not go in the order, so I'm going to try to go in the order, but I may not. But we are going to do the hydrocarbons first. What are hydrocarbons? What do they have? Only hydrogen and carbon. And alkane is not a true functional group, but we still list it on the functional groups, and that is C single bond C. Alkene, now you start telling me, alkene, C double bond C. Alkyne, what is an aromatic or a benzene ring? Give me the shape. Hexagon, and what's special about it? Single double rotating bonds, or that you might see the circle in the middle. Okay? So then we have, and these will not be in order probably. Tell me what an alcohol is. COH. C single bond OH. If I don't say double bond, then it's just a single bond. So COH. What is a thiol? That's when we drew in. CSH. CSH. What is an amine? C nitrogen. Now, if you say CNH2, you don't have to look for the NH2. Here's what I want you to look for. Just simply look for carbon and nitrogen. CN. That's what you're looking for to know that you have an amine. CN. What is ether? COC. And what's an alkyl halide? Don't tell me CX. C and a halogen. Now, what are the halogens? Fluorine, chlorine, bromine, and iodine. Okay. The next group is the group that contains the carbon double bond O, which is called the carbonyl group. So a carbon double bond O with the carbon also having an H on it. So we say C double bond O, H. Who is that? Aldehyde. So C double bond O, H is aldehyde. What is C double bond O with an N? Amide. Amide or amide. What is C double bond O, O? Go ahead, you're right, ester. Now, let me tell you what students have seen. I always thought of ester as a woman, that's the woman's name, and I always thought of ether as a man. I didn't really put it all together until students have kind of put it together in their method. COOC could spell what? Cook. Typically women cook. I'm not trying to say only women cook, okay? Feminists, don't come after me. I'm not saying that. I'm just saying that typically we think of the female cooking. So I always think of ester So that's COO, and I just put the C on there because it probably is another C somewhere. So C double bond O, O next to a C, that's ester. And I always think of ether as the man. Now, what are roosters called? So is that COC? There's the man. Okay? You all, that always kills me. Cock-a-doodle-doo. Can we not say a rooster is a cock? See, you all cannot say that. Roosters are called cocks. You've never had a rooster before, have you? I have roosters, okay? That's what they're called. But that's ether, COC. That's how you can remember ether compared to ester. All right, let's keep going. So I'm going to repeat that. So C double bond O is who? Ester. Amide is C double bond O N. Aldehyde is C double bond O H. Carboxylic acid. C double bond O OH. C double bond O OH. And ketone. C double bond O between two C's. Okay? Every day. I'm not saying every day we have class. I'm saying every day go over those. Okay? Every day go over those. Now then, in your or on your syllabus. Oh, before I forget, who left their calculator at the test? Somebody said, "Oh, she picked up my calculator." Did you get your calculator, or is this your calculator?
I never got it back.
There you go. But that one is yours, you think? That was left on the desk.
Yeah.
Not my desk, but a desk.
Oh, yeah, it looks right.
Okay. Sorry to interrupt all that, but I just remembered that all of a sudden. And pencils. We gained pencils, by the way. There's 2 pencils, and Jocelyn, there's your Scantron. There you go. I see. You can't call me a stealer. I did try to give Dakota the pencils, but he said those are cheap, and he didn't want them. So, all right. So 4.6 on your syllabus. When you look at your syllabus, and it says that test 5 is over 4.6 and then 11 through 18, if you've paid any attention to that. If you look at the online book, which I realize most of you aren't, but if you look at the online book, 4.6 is basically talking some about what this is right here. It just gives kind of an overview of organic, and then 11 through 18 is the organic sections in detail with biochemistry toward the end. So you're probably thinking, when you've looked at that syllabus, you probably thought, oh my goodness, we're having a test that's a final and a test, and it's over 4.6 and 11, 12, 13, 14, 15, 16, 17, and 18. That's insane amount of material. And I would agree. We're not going to cover every chapter in detail. When I started teaching this, what I did, because I knew that the majority of what we learn in 109, it's like 70% of it is general chemistry, 30% of it is organic and biochemistry. And so I had to decide, what do I want to teach from those chapters that I feel like is important, and I pulled material from those chapters. And the way I've organized it is we start off with an overview, and that's, if you look at these notes, you start to see you have just these blanks and all these functional groups that we're going to fill in information about. So we're going to do a complete overview of every one of the functional groups. Then we come back and start doing details and how they apply more and how to name them. I do that, honestly, I probably do it because that's how I had to learn it when I was reteaching myself, and I felt like that was a pretty good way to teach you all. At the end, we probably will have an additional bit of notes that I'm going to add to this that's going to be an overview more, and really just more practice of naming and looking at characteristics a little bit better, because I think that's missing in my notes, and I think I'm going to add that this time. But what we're doing now is just looking at an overview of organic chemistry. So what is it? It's the study of carbon compounds. And remember that carbon compounds are going to be covalent or molecular. They share electrons and there are no charges. They have much lower intermolecular forces, then ionic. Now, what were the 3 intermolecular forces? Anybody remember? Dipole-dipole was one of them. That was the medium one. What was the lowest? London dispersion forces, then dipole-dipole, then hydrogen bonding. Good job. So London dispersion forces is everybody that's a molecular compound has London dispersion forces. And that's why this says all have London dispersion forces, because all organic molecules have London dispersion forces. Dipole-dipole occurs when? When you have a polar bond. What makes a polar bond? Difference in what? Electronegativity. And then hydrogen bonding occurs with OH, NH, FH. Those are the hydrogen bonding scenarios. So most of these are, or all of these are going to have London dispersion. Some may have the dipole-dipole, and a few will have hydrogen bonding. But overall, compared to ionic, they're much lower intermolecular forces, which means they are going to have much lower melting and boiling points, which is why many of these are liquids at room temperature and some are gases. Most will be what in water? Say it again. Insoluble. They're going to be insoluble in water. Why will they be insoluble in water? Because water is polar and these are nonpolar. These are nonpolar. All contain carbon. Most contain hydrogen. And some organic compounds have what are called heteroatoms. And I'm skipping a line here. I should have flipped these. All contain carbon and most contain hydrogen, may also contain other elements than carbon and hydrogen, and if it's not carbon or hydrogen, it's called a heteroatom. The heteroatoms are usually nitrogen, oxygen, fluorine, chlorine, bromine, or iodine. Obviously, they could also be sulfur. The thiol has sulfur. And so, again, it's going to be a nonmetal that's going to be in it. Some organic compounds have chains and some have rings. That ring thing is weird because we've not experienced that and you won't in ionic compounds. To give you an idea of what I'm talking about, imagine, if you will, my pointy fingers here, that's a carbon, here's a carbon, here's a carbon. In other words, I'm making a triangle, okay? They can bond that way. The organic molecules can bond in rings. Ionic compounds can't do that, okay? But organic can. Carbon is so versatile. Carbon has 4 electrons in its outer energy level. It can do all kinds of things. It can share 4. It's amazing, honestly, what carbon can do, which is why we have all these different compounds of organic molecules, which is why there's a whole field of organic chemistry. Because there's so many opportunities for carbon to bond. And the other thing that carbon likes to do is carbon doesn't just like to be carbon in one other element. Carbon likes to be lots of carbons together. So you get this whole string or whole chain of carbons together, or you can get these rings that form rings with other carbons and make this whole ring structure. Remember the ones I was showing you Monday on those drug inserts? Did you remember seeing some of those drawings? And that every time you saw a vertice, that was a carbon. So it's all carbons together like that, and they can do that. That's something we haven't seen before. But it's the same thing as always as far as how many electrons do they want. What do they want? What does everybody want except hydrogen? An octet, which is how many? 8. So it's the same thing. All atoms want an octet except for hydrogen wants 2. And so this picture shows us the bonding patterns for the organic compounds or the atoms that are in them. Hydrogen will only have a single bond. Carbon is going to have 4 bonds. Nitrogen will have one lone pair. Oxygen will always have two lone pairs. Halogens will have three lone pairs. So the next scenario that I'm asking you to do is something very simple. Probably some of you say, why do we have to do this? It's just simply to get you back in the mode of Lewis structures. All I want you to do on this one is show me where do the H's go and what will be around the chlorine. So what do we do if we don't have enough electrons? We add H. So how many H's does this carbon have? 3. How many H's does this carbon have? And this chlorine, what did it say up here in our table? Has 3 lone pairs. And so that would be a complete Lewis structure for that organic molecule. Something that I have found is helpful is to go ahead, even though I haven't even given you the rules on naming yet, I'm actually going to start naming today. And I'm going to start writing names and starting to let you see these names as we go so that it will start making more and more sense to you the more you see. Okay? When we learned molecular compounds, we learned some prefixes. Do you remember what those were? Okay, good. Organic molecules have prefixes for the number of carbons. Most of them are the same thing we've already learned, except for the first 4. So the first 4 are the ones you're going to have to learn that you haven't learned before. And that is meth means 1 carbon. And this is all written down later. Don't write it down now. Meth is 1 carbon. Eth is 2 carbons. Prop is 3. And bute is 4. After that, they're what you already know. Pent is 5, hex is 6, hept is 7, oct is 8, non is 9, and dec is 10. But the first 4 are different. So when we name with the number of carbons, and then if there's something added on, we add it on to that parent chain of carbons. So how many carbons? We have 2. That's eth. The suffix is based on how the carbons are bonded together. How are these carbons bonded together? Single bond, so that means that they are an alkane. So ethane. But then what's added on to it? A chlorine. So the name of this is chloroethane. Chloroethane. Now again, right this minute, I'm not expecting you to be able to name that, but I'm going to just teach naming every opportunity I have. And I think that will help us in the long run to do that. The next drawing, tell me how many hydrogens the first carbon will have. Good. What about the second carbon? Pay attention. Only 1. Why? Do you see these double bonds? 1, 2, 3, 4. That means 8 electrons. If you put another hydrogen, that would be too many electrons. And then what does oxygen have? 2 lone pairs. Does it matter where I put the lone pairs? No, it doesn't matter. What, and I should have done this here. I'm going to go backwards. What functional group was this? What functional group was present here? Say it again. Well, actually, alkanes are not a true functional group. It's not an alkene because it doesn't have a double bond. What kind of element is Cl? This is an alkyl halide. This is an alkyl halide right there. That's an alkyl halide. That's an alkyl halide. Why? What is an alkyl halide? Carbon and a halogen. All right, what functional group is this? It's got the C double bond O with an aldehyde. This is an aldehyde. That is an aldehyde. I don't believe I have you all name aldehydes in this class, but I am going to go ahead and tell you the name of this just to get you in the habit of seeing and recognizing names. 2 carbons means what? Eth. Are they single bonded together? So that's ethane. And actually for an aldehyde, the ending is al, A-L. So the name of this is ethanal. Now we have to be careful when we write because this is not ethanol, this is ethanal. What do you think ethanol would have in it? Anybody remember? You've heard me talk about ethanol before. It's an alcohol. So instead of having the aldehyde, it has an alcohol. But this is ethanal. What is the functional group shown here? Who has a nitrogen? Amine. It's an amine. It's not an amide. Now, why isn't it an amide? There's no double bond O. It's the double bond O. Now, I know some of you are probably confused because you are thinking it's just a C single bond N that makes an amine. It could be a triple bond. It could be a double bond. It just means carbon with nitrogen. But if you have a carbon double bonded O with nitrogen, that's an amide. That's different. But any carbon with nitrogen is an amine. So that's an amine. Tell me what I need hydrogen or lone pair wise here. What do I need? What goes here? Good. Anything on this carbon? Nope. Why not? Look, it's got 3, 1, 4. And then what about nitrogen? 1 lone pair, because nitrogen actually has a lone pair. Nitrogen has a lone pair. Yes or no? I'm not going to have you name amines, and I know I'm not going to, so I'm not going to even show you the name on that. All right? How do we draw these? How do we draw organic molecules? We can draw organic molecules with just Lewis structures, which is what we have here. This is a Lewis structure. This is also a Lewis structure. So those are Lewis structures. Those are complete Lewis structures. All carbons are shown. All hydrogens are shown. Those are complete Lewis structures. This is what we call a condensed structure. I want you to look at that for a minute and see if you can figure out where that's coming from. Tell me where the CH3s are in the compound. You all are fast. I was pretty dense. I had to really study that for a while to finally get that. CH3s have to be on the ends. Why is it just CH2? Because it's bonded to other carbons. So when you write the condensed structure, what the condensed structure is doing for you is actually showing you what it looks like in a condensed version. Now, a condensed structure is not a molecular formula. What would the molecular formula be? It would be C4H10. Add it up and make sure I'm right. Do you see where I got that? If you just saw C4H10 though, you don't actually know how it's put together. You have to see it as the condensed structure to know how it's put together. Now I know somebody is thinking, well, wouldn't it have to be that's the only way it could be put together? Actually, no. It could be put together a different way. If I had this, let me cover this one up. If I had this, count that up and tell me if that's C4H10. Now, is this put together the same way as the other one? No, it's not. Now, you guys are faster than I was at this, I believe. But let me just tell you, if this is still not making sense, don't feel bad. You will need, for those of you that are struggling right now, you will need to spend time on this. Meaning, sit down and draw pictures. And literally go back and forth, back and forth. Draw this, then sit down and draw CH3, CH. Now what's attached to that? You can't see it. What's attached to this CH? Another CH3. And then what's attached to this C still? CH2. And what's attached to, or actually it was CH3. I lied. CH3. I was covering one up. So this is the condensed structure of this. Now some of you guys are seeing that lickety split. Me, oh me, I'd sit there for a while and look at that because I just wasn't getting it. But I do now, obviously. But it took me a while. I had to really study that. This cannot be further, well actually I lied. This can be further condensed. But before I show you the further condensing of this one, let me go back to the notes and show you the further condensing of this one. This could be condensed like that. Does that make sense? And that's what I wanted somebody to ask me that. Her question was, why could you not also just put CH3 in parentheses 2, CH2, 2? And that's the answer. This is a condensed structure. It has to show what it looks like structure-wise, meaning who's hooked to hooked. Who's hooked to who, I meant to say. You have to show who's hooked to who. And the way you were saying it doesn't show how it's hooked. Now, how you said it though, I wanted you to say that because go back to this one. Could this be CH3 2 CH3? Study that for a minute. What is this saying? There are two CH3s, both hooked to C. Is that true? Yes, it is. And this CH3 is hooked to that. See the difference in them? They're different. And again, sit down, go back and forth, back and forth, back and forth. Just keep going back and forth on that. And you'll see what's going on. All right? It's going to take some time though. You're going to have to just really play around with them for some of you. Some of you just see it, no problem.
There's 2 right answers?
The condensed structure could be this or it could be this, yes.
Condensed and then further condensed?
But it will be called condensed. It is a condensed structure. This is the condensed structure. This is a condensed structure. They both are condensed structures. They're both right.
So you wouldn't put like 2 of those like over the...
On an answer multiple choice, no. No. Yes.
For the further condensed one, couldn't you also write the CH3 parenthesis exponent 2 on the other side as well?
Absolutely. His question was, could this CH3 parentheses 2 be over here and the CH3 by itself be over here? Yes. Yes. Because look how this is. You could have said CH3 CH CH3 parentheses 2. Make sense? Some of you yes, some of you no. Sit down and look at it. Go ahead.
On the exam, would you give us like the Lewis structure and then like the multiple choice answer would be the condensed form?
Possibly. Possibly, yes. Possibly. What I'm trying to get you to do right now is, and this is what tonight, part of tonight is just start to wrap in your brain, carbon can be bonded to other carbons in all kinds of ways. And it is shown with that different bonding also in different ways. This is totally different than ionic compounds. Ionic compounds were exactly what they were based on charges and there was no other choice about it. Here, different thing. CH with CH3 in parentheses 3? Yeah. Yes. Really, it could be. Because that's saying all CH3s are bonded to the same carbon. Yes. Yes. Could be. So you guys are seeing it. I'm glad. I'm very glad you're catching on quickly. That's very good. Let's go to the one at the bottom of this page. This is also a Lewis structure. And I've already shown you part of what this is trying to show. This is a branch. Did my example have a branch as well? Yes. Nathan, if you can reach the light and want to see if you can rotate the bulb and get it to quit doing that, feel free. If you don't feel comfortable doing that, that's fine. It's up to you. Huh? That's okay then. I just know some of the folks up there are annoyed by it. It's up to you. But this is a true branch. What we have here is a true branch. This is a branch off of this carbon. I showed you a branch already because this was a branch. So you've already seen the branch. You've seen the branch off of the carbon. And what this is showing you, again, is what I've already shown. The branch needs to be shown in the condensed structure, or you can do it as I've already shown you, like this. So again, this is a condensed structure showing the branch with everything drawn out. This is the same thing just by showing both of these are on the same carbon. Is that making any sense at all, Mackenzie?
Yeah, I thought the one you had drawn on the back was that one, so that's why I was so confused.
No, the only difference is it's missing a carbon and 2 hydrogens.
I'm getting it.
Yeah. But both of those are correct condensed structures. Let me ask a question. If we had, let's say, 8 carbons together in a row, all single bonded to each other, how could you write that? What would be at one end? CH3, and then you would put CH2, and you would repeat that how many times? 6, because you already have the first one. Then 6, that's 7, and plus then at the end would be what? CH3. Or you could do CH3, CH2 in parentheses with a 6, CH3. Does that make sense? Okay. We will see these and practice them as we go.
Real quick. I'm sorry.
No, it's okay.
Okay, you know how like there's like the little C, oh wait, just kidding. Why is that little CH still there according to that CH part?
It's just, this is a basic way of showing you where they came up with CH2.
On the bottom one?
Yep, and this is showing you CH.
Just checking.
See, what they were showing you here is this is CH3. They just didn't repeat it here because they've already shown you. And that's where these are. Oh, actually, though, there is something here I do want to show you, too, that I was confused about. When I would see these drawn this way at the beginning, I would look at this and I would see the H and a C next to it. And I would say, but the H doesn't have that C next to it. Some of you know what I'm saying because you're seeing the same thing. Who's bonded to who? All the C's are bonded to each other. Who are the H's bonded to? C's. Even though, for instance, this CH3, are these three H's bonded to that C? No, they're bonded to that C. Again, my strong suggestion today, sometime, look at this, redraw that. Look at this, redraw that. Go back and forth, and I think you'll get it if you're not getting it. Another way to write these is with skeletal structures, also called line structures. And they are used for chains and rings. Line structures are used for chains and rings. And these will have, when you see a ring or a line structure, you make the assumption that there is a carbon at the junction of any two lines. That's why a few minutes ago when I was doing my triangle and I said right here is the carbon, that's what we were talking about. At the vertice or the end, that's where we have a carbon. Now here's what's really weird. Line structures don't have to be in rings. I could have this. And I'm going to count my elbows in on this game. Right here, and right here. How many carbons is that? 3. So this is a CH3, CH2, CH3. And that's how you draw it. You literally draw that. And that means CH3, CH2, CH3. Or we could also say it means this.
I see the three carbons. Where do you see the 3 H's?
You don't see them. You just know they're there because all of the, if there's nothing else, then it's H, which is what this is explaining. Mentally fill in the hydrogen atoms around each carbon to give it 4 bonds. But now if it's something besides hydrogen, it will be there. So anything besides carbon and hydrogen will be there. The heteroatoms, if it's oxygen, it will be there. If it's sulfur, it would be there. If it's a double bond O, it would be there. And then if there's something bonded to the heteroatom, like a hydrogen, it will be showing. So that's where we have this example here for you. This is a heteroatom. Here they used all the lines, but there the OH is showing. It's showing. When I learned this, I, at the beginning, had to literally put dots here to get it in my head that that's a carbon. And yes, I even drew in the hydrogen so that I made sure I really knew what I was doing. There's no shame in that, okay? If you need to sit down and draw in the hydrogens just to prove to yourself it is CH3, CH2, CH3, go for it. But the actual line structure is just that 3, or the little triangle without the bottom part. You can do line structures for chains, which is what this is. You can also do them for rings, which is what we see here. This is the complete Lewis structure. This is the line structure. Now, I don't want you to get this confused with benzene. Why is this not benzene? It doesn't have the double bonds. Good job. So this is cyclohexane, just like this is cyclohexane. We just aren't seeing the hydrogens. Obviously, does this make it cleaner? Sure it does. It makes it a lot easier to write. Your drug inserts that we saw, what did we see? Did we see the complete Lewis structure? Not at all. This is what you saw. This is what you saw. Here, cyclopentanol. Now, why is this called cyclopent? Either one of these. Why is this called cyclohexane? Because it's a ring and it's 6 carbons. So cyclo is for the ring. Why is it ane? Because they're all single bonded. Why is it hex? Because there's 6. Why is this cyclo? Because they're rings. Why is it pent? Because there's 5 carbons. Why is it ane? Because it's single bonded. Why is it OL? Who is that? Alcohol. That's an alcohol group. That was new. You didn't know that answer. That's an alcohol group. That's why it would be called OL. It is an alcohol. The functional groups we've already gone over. They are groups of atoms that have a certain function. And as we go through here, I'm going to try to pull out some real things, just like I've got on those drug inserts where we talked about those, that are continually, you're going to see certain drugs behaving a certain way or affecting a certain system in your body, and they have the same functional group every time. And that's the reason they're called functional groups. They have a certain function in the body. That's why they are called that. In this reading, some of you questioned, why is it called R? I don't know why it's called R. I do know that the reason they wouldn't call it C is because they don't want you to think it's just one C. It could be many C's. And so they're not going to call it just C because it could be more than one C. If that confuses you, put C there and just know it could be more than one if that's going to confuse you, all right? But R just means carbon or a group of carbons. Now, from this point for this period as well as Monday, we are going to go through all the functional groups with characteristics. In or on Blackboard, I think I showed you this Monday, a student had put together a study guide or a functional group study guide, and I put it on Blackboard for you. That already has much of this in it, but it would still be good to look at as well as today to go ahead and write them down. I've already said, and I'm going to repeat this, I'm going to talk to you about naming as we go, even though we're not even to that page in the notes yet. By the time we get there, you'll know it, and that's why we're going through it now. So we're going to go through the hydrocarbons first. What do you think I mean when I say hydrocarbon? What do they have in them? Only hydrogen and carbon. And if you haven't put this together yet, if they only have hydrogen and carbon in them, would they be soluble in water if they only have hydrogen and carbon? Yes or no, soluble in water? No. Why? Because they're nonpolar. Good. Why are they nonpolar? Because the carbon-hydrogen bond is what? Is there much difference in electronegativity in that carbon-hydrogen bond? No. So they're nonpolar. So the hydrocarbons contain only hydrogen and carbon, and therefore they are going to be insoluble in water. Now, I'll go ahead and put it C, single bond C, and it is not a true functional group. They are insoluble in water. We talk about them because they're so common. You will recognize some of these names for the alkanes. They use the ending -ane. So in their names, they use the ending -ane. And we say that they are a saturated hydrocarbon. Where have you heard the term saturated before when it comes to anything in your life? Fats. You've heard of saturated fats. We're going to talk about saturated fats, but what this is dealing with is very similar to the saturated fats. Saturated fats have no double bonds between the carbons. Saturated hydrocarbon has no double bonds between the carbons. They're all what? Single bonds. They're all single bonds. So a saturated hydrocarbon means it's all single bonds, and everywhere you can throw in a hydrogen, it's got a hydrogen. That's what that means. So saturated hydrocarbon, no, or I'm not even going to put no, let's just put all single bonds and saturated with hydrogen, meaning hydrogen is everywhere it could possibly be. Alkane, probably one of the most unique things about alkanes, or the most, maybe not unique, but known, is that they are the principal compound in fossil fuels. They are the principal compound in fossil fuels. Alkanes are the principal compound in fossil fuels. Now, what are the fossil fuels? Coal is a fossil fuel. Petroleum and natural gas. Does anybody know what natural gas is? It's not propane, but propane is used as a fuel, and let me rephrase that. I don't know that propane may be, well, I'm not sure where propane comes from. Propane, I'm not sure if propane is a fossil fuel or not, to be honest with you. Travis, you know all these things. Do you know? I don't know. I don't know. Methane is a fossil fuel. That's natural gas. I don't know if propane is part of methane or not. I know it's not part of methane. I don't know if it's part of natural gas. I don't know that. I need to look that up because I really don't know where propane comes from. But you have answered, if you're listening, some of what we're saying here. Alkane, listen to the ending, alkane, they are the principal compounds in fossil fuels. What is one of them we just talked about? Well, the for sure one, methane, and propane, we don't know for sure. But then start thinking of the ane things you've heard of before, whether they're fossil fuels or not. What's the other one? Xander. What am I doing with my thumb? What kind of lighter? Butane. You with me now? Butane? Is butane an alkane? Now, where does butane come from? I don't know. It may come from petroleum. I don't know. But I do know that your methane is natural gas, and that is a fossil fuel. If you go to your petroleum, and we're going to have a whole page on petroleum later and look at what comes out of petroleum, they are alkanes. Long chain alkanes, like lots of carbons. And methane too is one of them that you will also even be able to get out of petroleum. And so the principal component of fossil fuels are going to be alkanes. Those are the principal compounds. I'm not just saying one alkane, I'm saying all kinds of alkanes are in fossil fuels. As far as their reactivity, they are not very reactive. So alkanes are unreactive except in extreme circumstances due to no double or triple bonds. Are unreactive except in extreme circumstances due to no double or triple bonds. Now, what do double or triple bonds have to do with anything? Well, first of all, single bond, or carbon bonded to a carbon. What's on this carbon? Hydrogens, 3 of them, right? What's on this carbon? 3. Is there any place for anything else to add? No. So it's not very reactive, is it? No. There is one time or one situation where they can react, and it is, in my opinion, I would say it's an extreme circumstance. And if you've already thought about it, you already know they can do what? What do we use all those things I just talked about for? Don't just say heat. Fire. Do we burn them? Yes. How does a butane lighter work, basically? I'm talking the kind you do with your thumb. I'm not talking about the fancy long stick one. Those have an electronic igniter on them. I'm talking about the one that you roll. What's that? Is that friction? And it's a friction, it's something metal or flint or something, magnesium hitting something, and it's causing a spark, which does what to the butane then? Lights it up, catches it on fire. Okay? What do we do with methane in our furnace? Burning it, aren't we? What are we doing with... Are you okay?
Yes, I am.
Okay. Okay. So we burn methane, we burn butane. What do we burn? I already said it. We burn propane. What about that petroleum? Say it again. The petroleum is the stuff in your car that keeps your engine lubricated, but it makes something else that's in our car. No, that's the oil that keeps it lubricated. That's what I'm talking about. Say it. Gasoline. Gasoline is made from petroleum. What do we do with the gasoline in our car? Burn it. We burn it. So are all those extreme circumstances? All of those are extreme circumstances. And so in extreme circumstances, they will react. And that's what I want you to make a note of. Burning is an extreme circumstance. Or an extreme condition. Alkanes will burn. That's mainly what we use fossil fuels for, is to burn. The first 10 alkanes we have names for that you are going to be responsible for. And here are their names. And this is not showing up very good on the screen. Methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. It helped me to put the number of carbons over here next to the name. So one carbon, eth is how many? And then these names make sense because we've learned these before. Now, are we seeing this a little bit better? Look at the picture, and does this make sense? One carbon, why will it have 4 hydrogens? Because it's got to have the 8 electrons around it. Ethane, 2 carbons. Propane. Now, I want to show you something here. Look at the top of your paper. What did I draw up there when I drew that upside down V? Look who that is. Is that propane? That's propane. Make a note so that when you go back and study, you can ask yourself, why is that propane? And you'll say, oh, because it's all single bonds and because it's how many carbons? 3 carbons. This is the butane that's in the cigarette lighter. That's the butane. And then pentane, and it keeps going from there. Have you heard of octane before? Where have you heard of octane? You know where. Where have you heard it? In the gasoline for cars. What does it say on the fuel pump? The octane rating. The more expensive gas has a higher octane rating. You've seen that? So you've seen these words in life, you just didn't know what they meant at all until now. And that's what that's meaning. All right. Let's go to the alkene. Alkene. What is an alkene? C double bond C. C double bond C. When it says unsaturated hydrocarbon, what does that mean? Not single bonds. That's what unsaturated means. It's not single bonds. I mean, I say that's what it means. It's one way of thinking of it. If something is unsaturated, it does not have only single bonds. If something is saturated, it does have only single bonds. That helped me to get that in my head. Saturated, it's just all single bonds and it's full of hydrogen. Unsaturated means it's got double or triple bonds, which then keeps it from being completely full of hydrogen. In order to be an alkene, it has to have at least one double bond C. Could you have a string of carbons that are single bonded and then just one double bond? Yes, and that's an alkene. Could you have 2 double bonds? Yes. But you have to have at least one. In order to be an alkene, you have to have at least one. So it must have at least one, must have at least one C double bond C. What do you think about their reactivity based on what I just told you about the reactivity of alkanes? Are they more reactive or less reactive than alkanes? More. You're right. In fact, we say they're quite reactive due to the double bond. Here's why. The double bond can be broken and other elements can be added to the compound. This is called addition. That's not rocket science. If you add something to it, it's called addition. It's actually called an addition reaction. When the double bond breaks and you add other elements to the compound.
Back to the unsaturated, just so it's, you wrote not single bonds, but can you say it's like not only single bonds? Like
You could, yes, you could put not only, that probably would be better, to put not only single bonds. And or you could just scratch that and put unsaturated hydrocarbons have double or triple bonds somewhere in there. That's also unsaturated. The key is it's not only single bonds, it will have at least a double bond or a triple bond if it's an unsaturated hydrocarbon. At least one of something besides single bonds between the carbons. Because all we're talking about are carbon-hydrogen compounds at this point. And that's what can confuse you, because then you'll think, oh, those functional groups, that was C double bond O. And that's a double bond. But it's not a double bond between C's. And we are talking hydrocarbons, meaning only carbon and hydrogen. Unsaturated means there's at least a double bond or a triple bond between the two C's, or more, however many C's we have. Let me go back to this double bond between C's, or it could be a triple bond, which we'll talk about in just a minute. Why does that make it more reactive? So here, let's go back to this one. Here is our single bond, and you had the C, and you had the C, and you had CH3, CH3. Okay, can you picture that? All right. Is there any place for anything to hook on there? Nope. Everybody's saturated, completely full, nobody needs anything. Now, even if you were to break this bond, by breaking that, you've just broken the whole compound apart in that scenario. And it would be this true in anything like that. No matter how many C's you have lined up in a row, if you broke one of those bonds, it's a broken compound. It's not that same compound anymore. But now, let's take a double bond. And let's say that we have a string of C's, but right in the middle we've got this double bond C. The double bond can be broken. Now I'm going to do it this way. I had to do it this way for this morning's class to get it. And let me do it here. I'm like finger challenged today, okay? So 2 and 2, you with me? I'm going to do this one as a line though. Follow what I'm doing? So single bond here, and this is a single bond, so that's a double bond when I put them together. Yes? This means this. All right? Let me rephrase that. I need pictures. Okay. This is the same thing as this. Why? Because what's this? 2 electrons. Follow now? Okay. This means this. 2 electrons.
This isn't 2 lines, this is like 2 dots.
This is 2 dots.
Okay, not 2 lines.
No, not 2 lines. Sorry. I need
Just do like this.
This is like dude. Okay. Whatever those little moves are. Okay. It's my new chemistry move. Okay. All right. So, here we go. Are we all together? Okay. 2 electrons. Double bond. So a total of 4. Yes. Okay. Can this be broken? Yes. And when it breaks, what's it leaving out here? 2 electrons. So are those 2 electrons opening up opportunities for other atoms to come in? Because these 2 electrons now they're not bonded to each other anymore like they are still here. Now this one's back on this carbon and this one's back on this carbon. So what does that allow something to come in and do? Attach, which is called addition. So does that make it more reactive? Yes. Now that triple bond, is it even more reactive? Yeah, because you could break one of the bonds or two of the bonds and throw out 4 electrons waiting for things to come in. Now, something you might want to see in your head and go backwards to is this page. On the very first page that we had, this might help you see it better. Back here, this is where this is basically what I'm talking about. And I say basically, this is O, so it's not exactly the same. So I'm not trying to confuse you. But how many hydrogens did this carbon have attached to it? Only 1. Why? Because of the double bond. Now, you follow what I'm saying? If a double bond's broken, does that leave a lone electron down here that something else can add on to? That's what I'm talking about. That's what I'm talking about. Diana, go ahead.
What breaks like a double?
What causes the break? If something else is near it and it wants to bond with it and the energy's right, it can do that. And again, that's why it's called addition. That's why it's called addition. Certain halogens are very good about adding to alkenes. And they will do that under some just normal conditions. Some of them take sunlight or UV light, and they'll just add to it. Now, here, let me throw a word in you've heard of. Have you heard the term chlorinated hydrocarbons or brominated? Have you ever heard of that? Or fluorinated? Have you ever heard those terms with air pollution? The fluorinated hydrocarbons or the fluorinated, there's another word that goes with it. Those are words you may hear. And the some of the things that they fuss about with air pollution are those alkyl halides, and the reason it happens is because when these alkenes and alkynes get exposed to sunlight, it's easier for the fluorine and the bromine and the chlorine to come and bond to them. And that's one of the that's one of the components of air pollution. I'll try to find that more exact term, and I think some of you probably heard it. You probably have heard what I'm talking about. All right, so what are some common alkenes? I'm just going to give you one here, and then I'm going to give you two we're going to look at just for the sake of naming. But one of these is this, what would be the simplest alkene? How many carbons would the simplest alkene have? Two, just two. The simplest alkene would have 2 carbons. That is the simplest alkene. Who do you think this is called? Oh, I didn't tell you about the ending. I should have. I forgot to tell you. The suffix. What do you think the suffix of these is? -ene. Good job. -ene. The suffix is -ene. So what is the name of this? Ethene. Good job. Ethene. 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 Now my gripe. Here's my gripe for organic chemistry. Some of you would love to gripe about chemistry in general, but here's my gripe about organic chemistry. That is the proper name of that compound. But guess what? They have common names. And the common names often don't mean anything that we should think they mean. There are only 2 common names that I want you to learn, and this is one of them. Not ethene, that's the proper name. The common name for this compound is ethylene. The common name is ethylene. The common name is ethylene. Now, does anyone know what ethylene is? Which is ethene, really? Anybody ever heard of ethylene? Ethylene gas. It is a plant hormone. It's a growth hormone. It is something that brand new refrigerators have a little cartridge that absorbs the ethylene gas. It is also why you might have heard someone say, if you have, say, peaches or a cantaloupe or something that's not ripe, you put it in a paper bag and put a ripe banana with it, and it'll ripen faster. What's the ripe banana giving off? Ethylene gas. Ethylene gas is a plant growth hormone. I could also say ethylene gas is the gas that's given off to ripen fruit. Ethylene gas is actually or unripe fruit or produce is exposed to ethylene gas in certain situations to get it to ripen. They actually expose like a crate, say, of green tomatoes that are not quite ripe yet. They can expose that to ethylene gas and get them to ripen. That's why, have you ever had like tomatoes in the middle of the winter that just definitely don't taste like tomatoes? I mean, they are tomatoes, you know they're tomatoes, but they just don't taste quite right yet. Probably what had happened was they were picked green, and then the ethylene gas they were in a chamber of ethylene gas, and so they artificially, in a sense, ripened. And they just don't quite have that same flavor that they would have if they'd naturally ripened. But the new refrigerators, this is funny, the new refrigerators, if you get a high-end refrigerator or mid-range to high-end refrigerator, they come, most of them now, come with a little cartridge that goes in your produce drawer, and it absorbs ethylene gas. Now, why would they do that? Makes your produce last longer.
So is the gas given off by something that's already ripe?
I think it's given off in the process of ripening and when it's ripe. Both. So the banana, think how fast bananas ripen. I mean, it's like sometimes overnight, it seems like. They evidently are super producers of ethylene gas, which is why people will say put that in there. You can also just put the produce in a paper bag itself, and it's giving off its own ethylene gas, and so keeping it enclosed helps it ripen faster. But that is one of the common names I do want you to know. I want you to know what ethylene gas is. I want you to know what it's for, but the name is properly ethene. Another alkene that I just want to teach you a little bit about naming with is this one. Throw in the hydrogens there. Put the hydrogens where they need to be. What do I put on this carbon? This carbon? 1. Good job. This carbon? And this one? All right. When we name these, we actually have to count the number of carbons. How many carbons are here? 4. So who is that prefix? Bute. Metheth-prop-bute. Metheth-prop-bute. Just start repeating those to yourself. Metheth-prop-bute. So this is bute. Because it has a double bond, it gets the ending -ene, so it's butene. So we could say the name is butene, but that's not 100% correct, because you have to tell where the double bond is. And in telling where the double bond is, you number the carbons. And you number so that the carbon, or so that the double bond rather, has the lowest number. Meaning you can number left to right, or you could number right to left. That's unusual. We haven't ever seen going from right to left in the United States with English. It's always we go left to right, but we can here. Because the double bond is on this side, we are going to actually number in this direction. So the proper name is 1-butene. The proper name is 1-butene. Now, why is that the proper name? Why wouldn't it be 2-butene? Because it is the first carbon. It's on the first carbon. What if it were here? Then it would be 2-butene. What if it were here? It'd still be 1. Good job. It would still be 1. Why? Because you would reverse the order of numbering. You would reverse the order of numbering. In other words, here it is 1. But if you put it here, it would also be 1, because instead of numbering left to right, you would number right to left. That's exactly right. So in other words, could you have a 3-butene? No, there is no such thing as 3-butene. 3-butene is really 2-butene.
Oh, I know what you're saying, like 1, 2, and then on the other side 1, 2.
I mean, just so you would know how to name it, but I mean, I get what you're saying.
That makes sense. Is it like 3-dimensional?
It's like going from the outside.
Exactly. It's the same left to right, right to left. It can be, you can look at it from this direction. Yes. It can be, exactly. Yes. The question is, will it change if it has more carbons? Sure. If it has more carbons, then you could have a 2 or 3 or 4-butene, depending on how many carbons you have. Yes. Yes. But this one could only be a 1-butene or a 2-butene. You could not have a 3-butene. You can't have a 4-butene. That would be true. That would be true. That'd be true for anything. You could never have the highest number, because if it were all the way at one end, you would start numbering from that end. Okay?
So a certain like structure can have 2 different names, or does it have to?
One proper name. One proper name.
But one proper name could have 2 different structures, correct? 'Cause you could have.
It's really not any different. It's just the difference in how you draw it on the piece of paper. Yes. In other words, this is 1-butene. I could redraw it and put the double bond here and a single bond there. And that's exactly the same. You and I look at it differently, but it's exactly the same. It's not any different. Okay? Now, again, we're going to do a lot more of this. So if you're not quite getting it, that's okay. I want to show you something, though, that you will see later. And I'm showing you these to start getting you to realize what you're seeing when you look at these. You are never going to have to name a drug. Okay? But look at the name. Look at that name and tell me something on there that you see. Do you see prop? Do you see methyl? That's something we're going to talk about in just a minute. Do you see fluoro? Do you see difluoro? Do you see difluoro up there or not? You're not seeing difluoro right here. Here's fluoro and here's difluoro. Do you see those? Now look. See how that has a 9 on it? And it also has this 6 alpha. That is telling us that this fluorine is on a 9th carbon and a 6th carbon. And the 6 is what they're calling the alpha carbon. Here, this is what we're going to call methyl, which is a few minutes in the notes. This methyl is on the 16 alpha methyl. That means this one of these is the 9th carbon, one of these is the 6th carbon, and this is what they're calling the what? 16th carbon. What I'm trying to show you is, and this one may be too complicated, I may not should have shown you this particular one, and this one actually may not be the 16th carbon, it's more likely probably this one. I didn't even notice this one over here. This is probably the 16th methyl and the 16th carbon. What I'm trying to show you though, without trying to make it too complicated at this point, when you see in those long chemical names the numbers, that's telling you the carbon that that particular thing is on. That's what that's saying to you. So if you see 3-methyl, that means there's a CH3 group on the 3rd carbon. If you see 9-fluoro, that means there's a fluorine on which carbon? The 9th carbon. That's what that's meaning, okay? And again, we'll look at more of these that are a little simpler. I should have picked a better one. You don't right now at all. And on some of these, like this one, you would never be able to, I mean, I won't say you never would be able to figure it out. You probably could the more you learned about it. But in our class on this particular one, you may not have ever been able to figure it out. I gave you too hard of one. I should have picked the same one I picked this morning, but I didn't get it. Regardless, you're seeing real things with what we're doing. That's what I want you to see. I want you to know I'm not making this up. Believe me, I couldn't make this up. Okay? But I want you to realize it's out there. And you're going to see it. Let's look at the alkyne. The alkyne. What will the alkyne have? Must have at least what? One C triple bond C. Must have at least one C triple bond C. What will the suffix be? Yne. And it's Y-N-E. I was starting out wrong. It's Y-N-E. Suffix is yne, Y-N-E. Again, why is it called an unsaturated hydrocarbon? Because it is not only single bonds. It's not only single bonds, so it will not be saturated. What about the reactivity? What do you think? Oh yes, it's high reactivity. They're quite reactive due to the triple bond. Exactly. Just like the double bond. Right. The more it would be more reactive, potentially, because you have potential places for other atoms to come onto. But you're not going to have any more than this. That 3 is the limit. So they are quite reactive due to triple bond. Quite reactive due to triple bond, and I'm simply going to put C alkene above about breaking and adding. I'm not going to rewrite all that, it's right above. So C alkene above about breaking and adding. Something I haven't added until now, and I'm not going to go back and add it, I'm just going to talk about it here. The alkynes have a unique characteristic in that they are gases at room temperature. Alkyne, they're going to be gas at room temperature. The alkynes are gases at room temperature. What would the simplest alkyne be? C triple bond C. Who is that? Say it again. Ethine. Good. That's ethine. That is ethine. Another way to write it is this. Does that confuse anybody? It sure did me. No, because, if I'm hearing you right, no, because what's going on here? Is the H bonded to the C? No. The H is bonded to this C, and this C is bonded to that C with a triple bond. This is the same as this. Now, for me, I didn't like that. Why didn't I like it? Because I got really confused about that H being next to that triple bond. That bothered me. It took me a while to get over that. Sit down and really talk to yourself and explain to yourself that H is not the triple bond. The H is bonded to the C that's triple bonded to the other C. I am not joking when I say to you, if this is not making sense, you need to sit down, even if you don't know how to name at this point. Draw a bunch of C's, put in a triple bond or a double bond and the rest single bonds, and start putting in carbon, or hydrogens rather, then come back and do this. Draw the condensed. So that when you see this, it looks like this in your head. Or when you see this, it looks like this in your head. And that takes time to sit down and do that. This is the second, these two are the two compounds that have common names that I want you to learn. And this one's worse than this one. Acetylene. Ethine is commonly called acetylene. Right, these two. These two. These two are the common names I want you to know. Called acetylene. Does anyone know what acetylene is used for? No, but that's your thinking. You're thinking of the acetaminophen. Acetaminophen. Acetaminophen is the common drug name for Tylenol. That's acetaminophen. And the problem is that these common names don't necessarily have any similarity to them. So you, just because it's like you're thinking acetylene, acetaminophen because you've heard of acete something, then you may be thinking, well, does it have something to do with vinegar? Because that's like acetic acid. So where is this all coming from? Well, those common names necessarily don't have a rhyme or reason. In the real world, acetylene is used in welding torches. You may have heard of an acetylene torch. If you went to a welder and said, do you all use ethane gas? They would probably look at you and say, no, we use acetylene. But what is acetylene? Ethine. Okay? It's the same thing. It's the same thing. So acetylene is ethine. Acetylene is reactive due to the triple bond, but acetylene also can burn, which is why acetylene, also called ethine, properly called ethine, was used in miners' lamps. and I'm going to show you this reaction, and then I'm going to bring a miner's lamp on Monday and show you. But the miner's lamp reaction, the miner's lamp reaction is a really neat reaction. It's pretty sharp how this works. It uses calcium carbide with water to produce those products. Now I'm going to name the ones that you don't know. This is calcium carbide. We don't think of carbon making ionic compounds, and that's just because I didn't tell you it could. But carbon is a really unique element. Carbon can share electrons, which is what we're mainly talking about tonight, but carbon can also lose electrons to become negative, and it can also gain electrons. I lied. It can lose electrons to become positive, and it can gain electrons to become negative. So this carbon has to have what charge there if it's with calcium? What charge does calcium have? +2. So what charge does carbide have in this scenario? -1. Because there's 2 of them. Does that make sense? That's not something we've learned before. It's not something I would expect you to know. But here it does. So how did this work? Well, calcium carbide, when it's reacted with water, will produce. Now, this is the other funny thing. What is this? The way I've drawn it right here, it doesn't look like anything you know, but what is it? It's ethine. Now, what am I saying? I'm saying this is ethine, this is ethine, and that's ethine. Is this the molecular formula for ethine? Yes. Does this show how it's put together? No. But the condensed structure shows how it's put together, and then the Lewis structure, of course, shows how it's put together. But this is ethine, or acetylene, and calcium hydroxide. So how does this work? Well, you know what a headlamp looks like? A little flashlight headlamp? You know what that looks like? All right. Imagine where you have the bulb in the flashlight headlamp, that's like the globe. In that globe there's an orifice where the ethine gas comes out, and they would light it, and then it would glow. So in other words, they were carrying fire on top of their heads going into mines, because they had a small water tank that would drip down onto the calcium carbide, and when the water would drip down on the calcium carbide, what would be produced? Ethine, which is acetylene gas, and calcium hydroxide, and that acetylene gas would come out one of the orifices in that globe. They would light it, and so they could see. They had light on their head. And that's the miner's lamp. I have one. I'm going to bring it Monday. And that's the miner's lamp reaction. What has to be present in order for combustion to occur? Oxygen. What's a problem in mines? Not enough oxygen. So if their lamp went out, what did that tell them? Either they were out of water, they were out of calcium carbide, or there wasn't any oxygen. So they might try to relight it again, make sure it's full of stuff, probably fill that, shake it, they'd know. And if it just won't light, but everything's okay, then what does that tell them? Get out, because there's no oxygen. Okay? So it's pretty neat. It was pretty neat how they, whoever came up with that. I don't know who came up with it. It's a pretty neat scenario, though. The aromatic. The aromatic is also an unsaturated hydrocarbon. Why? because it's carbon and hydrogen and it has those double bonds. Those double bonds make it unsaturated. It is called the benzene ring. You could draw it this way. It's a hexagon. You could draw it that way. And I'm not the best artist by any means. That's pretty messy there actually. But the point is, let me do another one. Your two lines, those are the double bonds. That's what that means. Those are the double bonds. Benzene ring is what we call this. And it is unsaturated due to the double bonds. Aromatics are liquid at room temperature. What do you think about their reactivity? Quite reactive. Why? Double bond. Quite reactive due to double bond. You will not have to name benzene rings or aromatic, but I do want you to be able to recognize that an aromatic is present. And so I'm going to tell you the names you'll see. In names, benzene or the aromatic ring may be called benzene, of course. It may be called benzyl or phenyl. Those are some common names that you will see in these compounds. Benzyl.
Benzyl peroxide, have you heard of that? Isn't that like
Yes, that is, is it benzyl or benzoyl? It's in pimple medicine. Look it up. This is epinephrine. This is an EpiPen. What do you see in there? The name, read the name. Do you see that dihydroxyphenyl? What's the phenyl? Here's the phenyl. Are these the hydroxys? Is that making sense now? Does this have an amine in it? Look at the name. What's the name say? Do you see that methylamino? Where's the amine? Look right there. Do you see the carbon and the nitrogen? Is it starting to kind of make a little sense? Okay. Now then, the alkyl groups. The alkyl groups are formed by removing one hydrogen atom from an alkane. Basically, what we can say about alkyl groups is that alkyl groups hook onto other structures. The alkyl groups hook onto other structures. What is methane? Go back in your notes and look. I know you don't have all that memorized tonight. Go back in your notes and tell me what methane is. CH4. So one carbon means what? Meth. One carbon means meth. So methyl is CH3 hooked onto something else. I put question mark. We don't know what it is. It doesn't matter what it is. It's CH3 hooked on to something else. That's methyl. Ethyl would be two carbons and their hydrogens hooked on to something else. So we could write that as CH3CH2 something else. Now here, I want you to stop a minute and get this wrapped in your head. Why do I put CH3CH2 something else? Why don't I put the something else over here? What have we said about CH3? Where do CH3s have to be? The end. The CH3 has to be at the end. Propyl would be what? CH3, CH2, CH2, something else. And then obviously it keeps going from there. So when we have these structures, let me see if I can find one that's somewhat simple, and I'm not, well, let's just go back to this one. This is the fluticasone. This is the nose spray. Let's go back to this one. Now then, do you see this? See that right there? What is this going to be called? Now, let me explain this triangle. That's just showing you it's three-dimensional. It's the same thing as a line. These also are just showing you the three-dimensional. It's the same thing as a line. Don't get that, let that confuse you. So what would CH3 bonded to something else be called? Methyl. Now, let me go to something else. What's a double bond called? Alkene. What's a double bond called? Alkene. If there are two within the same structure, it would be called diene. Now look up in the name. Look right here. Do you see this? What do you see? Diene. Now then, this, if you wanted to sit down and really work on this, you could start to dissect this one, because that is telling us that number one has a diene, or has an alkene rather. That means that either this, or that carbon is 1. And if 4 is the other alkene, do you follow what I'm doing? So you could count 1, 2, 3, 4. Would that work? And this would be the 1 alkene. This is the 4 alkene. That means this carbon is what number? If this is 1, 2, what carbon is this? 3. Look right here. Do you see 3 oxo? Would that help us indicate that? You follow what you're doing now? You could, now again, are you ever going to totally figure it out? I won't say you won't ever, because you may become an organic chemist. But we're not going to go far, but I want you to start seeing this. That also tells us that the methyl that you saw, which I'm not, right there, the methyl, there's a methyl over here, there's a methyl here. We're not sure which one we're talking about yet. That could be the 16th one. Why do I say that could be the 16th one? Could you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15? That wasn't right, but you get my point? Okay? All right. We'll finish these sets. Like I said, bring the